defined for you what is a formal power series is, and then we talked about the radius of convergence of a formal power series. Okay, and I was telling you that you would be able to show that if you take any complex number z such that absolute value of z is less than r, where r is the radius of convergence of a n z power n, then this series converges. Okay, so were you able to show this one, this particular exercise? Yeah, could you do this? Anybody? Yes, no response. Anybody was able to do this or not? Okay, if not, anyway, I will discuss this in a greater context. Okay, so let me begin. What do I want to say? Okay, so first of all, this question about convergence of the power series. If you have seen that in the definition of the radius of convergence, I had taken a set S, S, which was set of all r bigger than or equal to 0, such that mod of n r power n was finite. I had taken this set, right? So in this set, of course, our formal power series was a n z power n, n bigger than or equal to 0. Sorry, here also bigger than or equal to 0. Okay, so here, of course, in the formal power series, I had a n, where a n's were complex numbers, but while defining this notion of radius of convergence, I started with this series a n r power n, where a n were all I took a n with absolute value, so mod of a n, and r was anyway positive. Okay, so that kind of should give you a hint that the convergence that we will see of a power series inside the domain of convergence is going to be something special more than convergence. So it's going to be actually absolutely convergent. Okay, so that's the first point, key point. And next, I had also told that for power series, like we are going to see them as examples of holomorphic functions. Okay, so therefore, we will need some stronger notion of convergence, just other than this absolute convergence and all. We will need something called uniform convergence. Okay, uniform convergence on compact subsets. So we will see how that is relevant. Okay, so we will see that power series is going to have uniform convergence on compact subsets, and therefore they are going to define holomorphic functions. Okay, so since you can individual terms, you can imagine a n z power n. This is just a polynomial or a monomial. So these are all power series. So when you take the infinite sum and the infinite sum is uniformly convergent on compact subset, you get holomorphic function. Okay, so this is something which we are going to get for the power series. So what we are going to see means, like, so what I'm going to do is that I'm going to introduce one particular notion of convergence which perhaps you have not seen before. Now this particular notion of power series is going to take care of all these things. Okay, so it's going to take care of absolute convergence, it's going to take care of uniform convergence as well. Okay, so let me begin with that notion of convergence, and then we will see how means we are getting that for our power series. Okay,
ये तो कोई जब
okay. So let me give the definition. So definition. So the convergence which I am talking about is called the normal convergence. Okay, you will see that this is one convergence which is uh, easier to talk about, because means like, or like it's convenient to have this notion in place, because this takes care of both absolute convergence and uniform convergence in one go. Okay, so let me define what do I mean by normal convergence. Okay, so normal convergence of infinite series. So let, or series of function. So let fn from x to c be a sequence of function. So you have done sequence of function in real analysis, right? Yeah.
Yes, sir.
So similar thing only. So I have a sequence of function defined on a set x. Okay. So now I am going to define some quantity called norm of fn. Okay. Define norm of fn. So this, many of you probably have seen. This is the sup norm. Okay. So supremum mod of fn x as x varies over capital X. Okay. So this is norm of fn x. Now we say fn is normally summable on x, or we say summation n bigger than or equal to 1. So let us say here I have a sequence n bigger than or equal to 1 or bigger than or equal to 0, doesn't matter. Let's say right 0. So say fn is normally convergent, anything you can use if the series of real number, or rather non-negative real numbers, let me write, summation norm of fn x is finite. Okay, so what do I have? I have this notion of normal convergence. So this is what it is saying. It's saying that I have a sequence of functions on a set, and by norm we mean the supremum of the absolute value of fn of x. Okay, and then I am saying that fn is, I'll call that fn is normally summable on x, or summation n bigger than or equal to 0, fn is normally convergent probably on x if the series of non-negative real numbers, this one, of these real numbers, fn's, norm of fn's, those ones are convergent. Okay, so is the definition clear?
Yes, sir.
Yeah. Okay, so now once, if this is clear, then you should be able to tell me how does this follow. So exercise, normal convergence implies absolute convergence and uniform convergence. Okay, so what I am saying is that suppose I have a sequence of function, then which is normally summable, or the summation fn is normally convergent, then that will imply that absolute value of fn x for any given point x, the sum of absolute value of fn x is convergent, and the actual sum, summation n bigger than or equal to 0 f of n, is a uniformly convergent series of functions. Okay, so how do I get that? How do I get this exercise? Tell me. Yeah.
So the term which are using in the definition is also for used for absolute convergence and uniform convergence. That's why.
Okay, so for absolute convergence, this should be easy because I have supremum over here anyway. So if I take any at any point mod of fn of x, so that is dominated by the norm of fn, and therefore you can use comparison test. Each, all these terms are non-negative, so you get absolute convergence. But how do you get uniform convergence?
So since it is supremum, therefore it is free from it.
Yeah, so but you need some argument. It's supremum means in uniform, but how?
So then it will not depend on x
Okay,
because
it will not
supremum is
be on x. Fine, that's true. Yeah, but if you want to give one line answer, you this follows from something called, if you have heard of, Weierstrass M test, right? Isn't it? Have you studied Weierstrass M test?
Also,
Yeah, so suppose you have a sequence of functions fn, and each of which, like if you take, if there exists some mn such that mod of fn is always bounded above by mn, and summation mn converges, then fn is uniformly convergent. Means sum of fn is uniformly convergent. Okay, so therefore you see that this notion of normal convergence is one which takes care of both these two things. Okay, fine. So that's good. Now what we are going to do is that we are going to prove that the convergence of formal power series inside the domain of convergence, or let me, I will define what it is. Inside the disk of convergence is going to be normal convergence. Okay, so next theorem, probably theorem, let summation n bigger than or equal to 0 a n z power n be a formal power series and r bigger than or equal to 0 be its radius of convergence. Then on B0R, that is on this open ball, or yeah, the power series converges normally. Okay, so the convergence is going to be normal convergence inside this open ball, and in fact probably I need to be slightly careful. Just let me see. Okay, so yeah, I will rather say the following. So I will say that then on let's say B0R, the power series converges normally for all 0 less than or equal to R less than R. So I just have to be slightly careful with the boundary, so I'll be able to show this one. Okay, so that inside the ball, inside the radius of convergence, you will say that your function converges normally. Okay, the ball B0R is called the open domain of convergence, or open domain, or disk, whatever you prefer, convergence of summation in Z ball. Okay, so this is what I am going to prove, that the moment I have this radius of convergence R, and then if I take something which is slightly smaller, I'll always be able to show that inside that small ball my convergence is going to be normal convergence. Okay, so of course the convergence, as I said, I had already told you in the last class, the convergence is not so difficult to prove, because the convergence is essentially comparison test. Okay, but I am more interested to prove this normal convergence, because I told you already that we would like to have that our power series defines holomorphic functions. Anyway, okay, so let me begin. So I am going to begin, like I'm going to prove this by using a lemma, which is a lemma due to Abel. Okay, so Abel's lemma. So what is Abel's lemma? Abel's lemma is that let R and R0 belongs to R such that 0 less than R less than R naught. Suppose there exists a real number such that, suppose there exists a real number such that 0 is less than R less, sorry, there is real number M number m such that what is the property of this real number? That mod of an r naught power n is less than or equal to m, okay, for all sufficiently large n, for all sufficiently large n, then the series summation a n z power n converges normally for on b 0 r. Okay, so what am I saying? I am saying the following statement by Abel, so which is a very powerful statement, but you will see that the proof is very simple. Okay, so what it says that I have, let's say, two real numbers r and r naught such that 0 less than r naught, and what I am saying is that if in case there exists a real number m such that for sufficiently large n, mod of n r naught power n is less than or equal to m, then this guy, the actual power series that I have started with, is going to converge normally on B0R. Okay, so in fact you can even write B0R closure. Okay, so you can even write closed for, doesn't matter. Okay, so here also you can put closed if you wish. Okay, so anyway, because your little r is strictly less than capital R. So I have this lemma of Abel, and that's going to give us this proof. Okay, so let us first prove Abel's lemma, and then we will see how it gives us normal convergence. Okay, so you see already the statement of Abel lemma itself has normal convergence on some ball B0R. Okay, this little r being smaller than capital little r naught. Okay, so let me first give you the proof of Abel's lemma. Okay, now the proof of Abel's lemma is not so difficult. Okay, so I want to prove what? I want to prove that this guy converges normally on B0R. So I have to take the norm of each of the term, and then I have to make sure that when I take the infinite sum, that should converge. Okay, so we are going to take the norm. Okay, so let z belongs to B closed R, that is mod of z is less than or equal to r, so I am taking this. Hence, if I take mod of a n z power n, if I take this mod, so this is less than or equal to mod of a n r power n, and which I can write in the following way, that this is less than or equal to mod of a n into r naught power n times r divided by r naught power n. Okay, so this is actually equality. You agree to this?
Yes, sir.
Okay, so now notice here that I know that this guy, for sufficiently large n, this guy is bounded above by m, correct? Yeah, so this is less than or equal to, I can write m times r divided by r naught whole power n. Will you agree to this?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So therefore, what I can say that this is true for all z in B0R, right? So hence mod or norm of a n z power n, when I take the norm on B close 0 R, this guy is less than or equal to m times r divided by r naught power n. Okay. Now can I now do I see that summation a n z power n is normally convergent on B 0 R?
Yes, sir.
Why?
Yes, sir.
By conversion
Sir,
comparison test has
right side.
Sir, geometric
R.
C.
Absolutely.
R is less than R naught.
Sir, right side.
Very good. Very good. Yes, exactly. Whatever all of you are saying, that's correct. R is less than R naught. So this one is going to give me geometric series with the ratio which is less than 1. So therefore, I can say hence since R is less than R naught, by comparing with geometric series. We get normal convergence of A in Z power n on B0R. Okay, so on this set I get the normal convergence. So that one is rather easy to figure out. Fine, so I have this one, and now I need to prove the actual theorem that I have said about this normal convergence. Of course, I'm going to use Abel's lemma. Okay, so this is what I am going to prove. So let me see if I can do this. So proof of theorem. So proof of theorem. So how do I prove that? Can you suggest anything? How can I prove the actual theorem now? Yes.
You have to find
In
such
the bowl 0R the power series is convergent, then that this term is bounded by some positive real number.
Which R? Capital R, small
Yes.
r? Which R do you want to take?
Capital R.
Okay, so there will be a problem there because I said R is the radius of convergence. So by definition, what
Yes.
was the radius of convergence? By radius of convergence, capital R was the supremum. Okay, supremum of all these values. If you see supremum of S, so capital R was supremum of this capital S, right? So that means that does not guarantee actually that on capital R, like if you substitute over here capital R, that the series is going to be convergent. Okay, that's not going to happen. Okay, so there could be possibility that it is not the case. Okay, I will write down some examples as I had sent later. So we will see that. So at if capital R is the supremum of this set S, it actually does not guarantee that at capital R I will be having absolute convergence. Okay, so that I don't have that luxury. So what we are going to do, we are going to of course use that fact, but we are going to do something slightly like some small trick, and we will be able to do that. Okay, so let's see. So we have what? We have R is bigger less than capital R. Okay, so 0 less than or equal to R less than capital R. So what I am saying is the following. So find R naught in R such that 0 less than or equal to R less than R naught less than R. Can I do this?
Yes.
Yes,
Yes,
sir.
sir.
Yes, sir.
okay.
It's possible, right? I can just take, for example, R naught to be little r plus capital R divided by 2, for instance. Correct? All of you agree that I can do this?
Yes.
Yes, sir.
So once we do this, then what can I say now? Now what Abhishek was trying to say, if we do that, so we know by definition. So what do I know by definition? So let's say capital R is supremum of S and little r naught is less than capital R. So that means what? Little r naught cannot be the supremum. So eventually, in fact, little r naught is going to be inside the set S. Okay, so because anyway we have seen that the set is an interval, and little r naught cannot be a supremum of this set, which is smaller than the supremum actually. So therefore, at little r naught, what can I say? I can say that
There exists M.
yeah, no, but first of all, what can I say? That there by definition of R, we get first of all,
Convergent.
yeah, exactly, we get that this one is finite. Correct? Agreed, all of you?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
So once we have that, call this sum to be to be m. If I call this sum to be m, now you notice each of the individual terms a n r power mod of a n r naught power n, each of them are going to be less than or equal
less
to
than
less than
Okay.
m, right? So this sum I am calling to be m, and I am getting that each of them are less than or equal to m. Hence, by Abel's lemma, we have normal convergence on B close 0 R. Okay, so you see that the proof is rather very easy. Okay, and in fact, yeah, so this is what it is. And in fact, I had did I mention this over here? Yeah, so this convergence is normal convergence we see. Okay, fine, all of you agree to this?
yes.
Yes, sir.
Yes, sir.
Okay, so now here I would like to, of course, I had said this in the exercise itself, but I would also like to point out uh, this I did not state in as part of the theorem, but let me write it. Note, yeah, note that if mod of z is strictly bigger than r, then summation a n z power n. So what can I say? Yeah, so this is not bounded. Yeah, so then mod of a or n does not converge. Okay, so this is what I want to show. Okay, so I want to show that
Thank you.
I want to yeah. So I want to show that this does not converge. Okay. Now what we can do is the following. We can say that this does not converge for a very simple reason. I will say that the terms, individual terms over here, so that sequence itself is not bounded. Okay. So if the sequence itself is not bounded, then it's not possible that our sum can be convergent. Okay. So we show the sequence a n z power n is not bounded. Okay, so do you all agree that if this sequence is not bounded, then we will get that
Yes,
the
sir.
infinite sum does not converge? Okay, because if the
Yes.
infinite sum converges, then we will know
Yes,
that
sir.
the nth term goes to 0, but I am claiming that the sequence itself is not bounded. Okay, so now how do I show that this sequence is not bounded? So suppose, so let us prove it by contradiction. So suppose there exists m positive such that mod of a n z power n is less than m for all n bigger than or equal to 0. So suppose this sequence is bounded. Okay, now if this sequence is bounded, what I can do is the following. Note, if we take some little r such that capital R is less than little r less than mod of z, then by Abel's lemma, we have um, summation a n z power n. I should write the power series. Let me just write the power series. The power series converges normally on B close 0 R. All of you will agree to this? Yeah?
Yes, sir.
Yes.
That,
Yes, sir.
that is what we get from Abel's lemma. Now, if it converges normally, so of course it converges. We have seen it converges uniformly, so therefore it converges pointwise. So in particular, we have, and means in fact we have absolute convergence. We have this one is finite. Do you agree to this? Yeah, because normal convergence implies absolute convergence, and it also implies pointwise convergence by means of uniform convergence. So therefore, I can say that this sum is finite. Correct?
Yes.
Now,
Yes,
Yes,
sir.
sir.
now do we get a contradiction?
Yes,
Do
sir.
we get a contradiction? What is the contradiction?
Yes, sir. So
This
the
one.
series is convergent for mod Z less than
Then
capital R,
small r
but
will be
here R.
supremum of the set, but capital
But
R is the
Yeah, so that's very good. So this contradicts that R is the, actually I should have written, let's say, R not over here, because probably it's too many things like this. Okay, so this contradicts that R is the supremum of the set R bigger than or equal to 0, such that mod of n R power n is finite. Okay, so clearly I have some quantity R naught which is bigger than capital R, but the series is converging there. So clearly capital R cannot be supremum of this set. So we are getting a contradiction. Okay, so therefore this sequence itself, forget about convergence of the series. The sequence does not even converge. It's an unbounded sequence. So there is no question of the series being convergent. Okay, so this is what we have. So we see that indeed we have a very strong notion of convergence inside this disk of convergence. Okay, so now I was telling you about this various
Excuse me, sir.
yes.
Sir, we have shown here that this series is not absolutely convergent, but we want to show conditionally convergent.
No, Harsh. I have proved that the series does not converge because I have shown that the term of the series itself, they are not bounded. If they are
Okay,
not,
okay, sir. Okay, sir.
if not bounded, how can the series be even convergent, right? Because if the series is convergent, whether it's absolute, not absolute, I don't bother. The nth term must go to 0, right? So that is what is not happening here.
Okay, sir. Okay, sir.
The series itself is, the sequence itself is not bounded. So I have got that. So we see that this does not converge absolutely, means like absolutely or conditionally, in by any means this does not converge. Okay, fine. So this has been one point of debate for all of us for some time, that what happens at the radius of means exactly, if I mean, so we understand that there is this radius R, capital R, so that inside that once you come inside, for example, if you look at this theorem also, so once you come inside, you take any point in open V0 capital R, that at that point the absolute value is going to be strictly less than capital R, and then suitably you can choose your R, little r between, so you, no matter what, so if let's say Z, mod of Z is less than capital R, so choose for example, mod Z less than little r less than capital R in such a way, and then you will get absolute convergence, or all kind of convergence at the point Z. Okay, so inside the disk of convergence we have a very nice feature, but now the question is, what can we say about the points on the circle of convergence, in the sense on that particular circle. For example, if I take mod Z, uh, if I take, for example, mod Z is equal to R itself. Okay, so let us see some examples and try to understand. Example. Okay, so we had taken already, you had seen this example the other day, Z power n bigger than or equal to 0. Okay, so we had seen that if I take this, so here, what was the radius of convergence? Tell me, what was the radius of convergence?
One.
This radius of convergence was 1. And this open, what was open domain of convergence?
Mod of z is less
Closed
than
to
1.
two.
Strict.
Close -1 to open.
Sorry.
Mod of z is less than 1.
Less than 1.
So this is open domain of convergence.
Circle of send to 0.
Yeah, so this one is the open domain of convergence. And now tell me that if I, for example, take any point on the circle of convergence, like for example, now if mod z is equal to 1, okay, so what can we say about summation n bigger than or equal to 0 z power n?
It will not converge.
Diverge.
Divergence.
Okay, I don't generally use for series the word, or for sequence generally I don't prefer to call it divergent. Okay, so rather I prefer to say that this series does not converge. Okay, so this does not converge. Okay, so can you give me a reason, quick reason why this does not converge?
Sir, in case
And
of
that
1,
term
it will
does not
go,
goes to 0.
Yeah, Harsha, you were saying something.
in case of 1, it will go to, means the series will go to infinity. In case of 0, 1, it will be oscillatory sequence.
In case of 0, 0, 1 means here I have absolute value is always 1. I am taking this sequence more z power n. Okay.
So it doesn't satisfy necessary condition of convergence.
Yeah, so what Mahesh says, that is the key point. This does not converge because exactly like the last slide, here the nth term itself does not go to 0. Okay, so no matter what point you take on the circle, it will never converge. Okay, so this does not converge. Does not converge for all as mod z equal to 1.
Mod z.
So for all z such that mod of z is equal to 1. Okay, in fact I can write greater than or equal to. Anyway, you know, for greater than 1 it will not converge, but also for greater than or equal to 1 this does not converge. All of us agree to this?
Yes.
Yes.
Great.
Yes, sir.
Okay, so
Yes, sir.
therefore, what do I see that so in particular if I take so here radius of convergence is 1. So for example, if I take 1 power n bigger than or equal to 0, this does not converge. Correct? So even though I have some value as a radius of convergence, that does not mean that at that particular, like if I replace r means if I replace z by r, it does not guarantee convergence. Clear? Okay, somebody was trying to, Abhishek, you wanted to use the capital R for convergence. Now is it clear from this example that
Yes, sir, clear.
and whatever is our value of radius of convergence, my series might not converge then. Okay, so this is first example. Let's come to another example. Let us take n bigger than or equal to 0, 1 upon n z power n. Okay, so that's my series. Next one. Okay, so here can you tell me what is my radius of convergence?
Also 1.
Okay, so radius of convergence, somebody says this is also 1. Okay, so how do I get this one is radius of, I don't use any formula at this moment, if even if you know that. Just from whatever we have discussed so far, can you tell me that the radius of convergence is going to be equal to 1?
Sir, supremum.
Sir.
Sorry? Yeah, I want to know why the supremum is 1. That is what I precisely want to know. Yes? Tell me, why is it like this?
So it is normally
If-
convergent for in the ball 0, r where r is less than 1.
Yeah, okay, so again, why that is true? This is a statement which I understand that you get it
If
from.
we take
Okay, so for example, tell me what is this set S. What was that? Yeah, R bigger than or equal to 0, such that summation 1 over n r power n bigger than or equal to 0 is finite. Tell me what is this set?
Close 0 open 1.
Close 0 open 1. Very good. So this set itself is close 0 open 1. If we agree to that, we are automatically getting that the radius of convergence is going to be equal to 1. How? So first of all, we can clearly see that r equal to 1 does not belong to this set. Agreed? R equal to 1 does not belong to this
Yes,
set.
yes, sir.
Yes, sir.
Yes.
Because
Yes,
harmonic series does not converge 1 upon n, so therefore r equal to 1 does not belong to this set. And now you will be able to show that given any r which is less than 1, this series converges. Correct? Yes, given any r which is less than 1, this series converges. Why? Quickly, can you tell me?
So Abel's lemma.
Sir,
No, not even Abel's lemma. Like for that I need what is radius of convergence. Here I am trying to establish that 1 is the radius of convergence. So can you tell me why every r which is less than 1 belongs to this set? Just by ratio test, right?
because
Yes.
Yeah, if you just take do ratio test for r which is less than 1, you will see that the ratio of the n plus 1th term divided by nth term is going to give you the limit to be equal to r which is less than 1. So therefore by ratio test you will get this set is this one. Agreed? All of you agree to this?
Yes.
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 Yes,
So
sir.
now the moment I have this guy like closed 0 open 1, so I understand radius of convergence is equal to 1. Very nice. Okay, so now again let us try to imagine what happens on the disk of convergence. Okay, so let mod of z is less than or equal to 1, sorry, mod of z is equal to 1, and I try to understand what happens to the convergence of this series on these points. Okay, so what can we say here? For example, so let us take 2 points. We already we know that summation 1 over n does not converge, or rather diverges to infinity. Okay, so this does not converge. So clearly I find a point where the series does not converge. Fine. Now can I find another point where the series actually converges on the circle of radius 1?
Yes, sir. -1 is 1.
Okay, so for example, now if z is equal to -1, then we know n bigger than or equal to 0 minus 1 power n divided by n converges, right? So this you have seen already in your real analysis or infinite series class, that this converges by alternating test, right? Okay, so therefore now I have an example where I have different behavior in the boundary points. That there could be point where the series is converging, and there might not be points where the series is not converging. Okay, is this clear? So this
Yes.
Yes, sir.
is exhibiting two different behavior on the circle of convergence. Okay, so on that particular circle, at some points it's convergent, at some other point it is not. Fine, that's good. So now let us take another series. So another series which I am interested to take is the following one: n bigger than or equal to, sorry, here I was writing 1, but let us make it 1 okay, because I have 1 upon n. So 1 upon n square, all these are n bigger than or equal to 1. Okay, so n square z power n. So let us take, this is my sequence, and this is my power series, and then again what is my radius of convergence? So
One.
this is
1.
1.
going to be radius of convergence is going to be 1. And now you tell me what is this set S in this case?
Zero.
Close 0 1.
0, close
0 to 1, close 1.
This one, in this case we are claiming that this is our set, and therefore the radius of convergence is 1, which is the supreme one. Very natural. Fine. Okay, so now how do I see that this is closed 0 1? So at the point 1 we agree that this series converges. Okay, so therefore the supremum is at least one. Okay, is it clear? So clearly closed 0, closed 1 is subset of S. All of us agree to this?
Yes, sir.
Yes, sir.
Yes.
sir.
So now how do I get that there are no other points outside this this interval in S? Okay, so how do I show this?
Take any r greater than 1, so then
Yeah, then how do
r
I?
does not belong.
Use ratio test.
Then power series doesn't converge.
Absolutely. So exactly again the ratio test. So if r is bigger than 1, then we know 1 over n square r power n bigger than or equal to 1 does not converge, or rather diverges to plus infinity, does not converge by ratio test, right? So if I take the ratio of n plus 1th term divided by nth term, it's going to give me r, which is strictly bigger than 1, so it will not converge by ratio test. Okay, so here I see that capital S is closed 0, closed 1. So hence now tell me, if mod z is equal to 1, then what do I get? What can I say here actually?
Finite.
The series converge.
Series is even absolutely convergent, right? Because if I take z power n divided by n square, n bigger than or equal to 1, if I take absolute value, this is just going to be 1 over n square, n bigger than or equal to 1, and this one is finite. Okay, so here we see another case. Here what is happening is that at every point on the circle I have my series to be my power series to be convergent, or rather absolutely convergent. Fine. Yes, all of us agree to that.
Yes, sir.
Yes.
So we have seen that in on the boundary, our case, like the possibilities can range from one extreme to another extreme. One extreme being that there are no points on the circle where the power series is going to converge, to the other extreme that on all the points on the circle the power series is going to converge. Is it clear?
Yes.
Yes.
So we can have anything in between, so you must be careful. So because when we are going to work with some radius of convergence of some unknown power series, we do not know how the function actually, how the infinite series actually behaves on the circle. So therefore we have to be slightly careful about means whether we can take we can substitute the value of the radius of convergence in the power series or not. So those kind of things one has to be slightly careful about. Okay, so it depends completely on the power series, and it can it can vary from case to case, and like we can have extreme possibilities. Okay, and if you remember, I had talked about one notation. So here this B0R, so capital R open. So this I was calling this open disk of convergence. Okay, of course here everything that is there, I am having my function to be convergent, or the infinite series to be convergent, or power series to be convergent. And once we take any point outside the closed disk, the series is not converging. And in some cases also we have seen that there might be points on the boundary where the infinite series will be convergent. Okay, so for example, in the last case, on all points on the boundary or on this unit circle, on all points this power series is converging. Okay, but we will not be interested so much about the points on the boundary. Okay, for a very simple reason. Okay, so let me try to draw a picture. So let's imagine this is our circle. Okay, or maybe I draw the coordinate system first and then we draw the circle. So let's imagine we have a circle, and now I have a point over here. Okay, so I have a point, let's say some z naught, which is on the boundary. Okay, now why I am not really bothered about whether my power series converges there or not is the following. See, once I look at this point, even if the power series is convergent there, I will not be able to say that my uh, function, or like the function which is defined by this power series, that I'll not be able to say that that particular function is going to be holomorphic there. Why? Because to have holomorphicity at z0, I at least need a small circle around z0 where my function should be differentiable,
differentiable.
or in other words, the function, at least whatever this, since I am having it in terms of the series, that series should to start with at least converge, right? Now no matter how small neighborhood I wish to take around z0, it's always going to cross this circle and it's going to go outside. And we have already seen that if I take any point for which mod z is bigger than r, there the series does not converge, right? So therefore, from that, then from the perspective of differentiability or holomorphicity, we see that these points on the circle are not so interesting, right? Do you get my point, what I am saying? Yeah.
Yes, sir.
So these points are not so interesting in that way. So that is the reason why we will not be that bothered about points on the circle, what is happening. Of course, for better understanding, we can try to figure out, okay, whether it has, like whether we have convergence or not, or things like that. But as far as studying this holomorphicity and all this, we will not be much interested about these points on the circle. Yeah. So that's the reason why I had defined this quantity, which is the like this notion, which is the open domain of convergence of a power series. Okay. So that means now if I take any point, for example, whatever points, something which is in between, I'll always be able to find some circle around this which will be inside that, right? So therefore it does not really matter whether I means like, as long as I am inside the circle, I'll always be able to put it inside a ball which is strictly lying inside my open domain of convergence. So therefore there is a clear distinction between points which are in the interior and which are in the boundary. Okay, so we will not be so interested about points in the boundary. Okay, fine. Yeah, I hope this is clear, whatever I have said. Fine, so let me transport this picture to the other page. Okay. Okay, fine. So now I have, of course, told you how to figure out this radius of convergence and all this set capital S and figuring out the radius of convergence. So let me give you a formula for the radius of convergence so that you can directly calculate the radius of convergence just by looking at the terms of your coefficients of your power series. Okay, so this one probably you have already seen, many of you, formula of radius of convergence. It's a formula for radius of convergence. Okay, so this formula is due to Hadamard. Okay, so what is the formula? The formula is the following. So for a formal power series, summation n greater than or equal to 0, a n z power n, its radius of convergence, R is given by the formula. So what is the formula? 1 upon R is equal to limbs as n tends to infinity mod of n equal to the power 1 over n. Okay. Just a second, I'm getting it. Okay, so I have this formula. So some of you have you must have seen this, right?
Yes.
Yeah,
Yes,
this
sir.
formula.
Yes.
Okay, so in case you have not seen this before, so I'll just briefly recall how the limb soup is defined. You know, right, how the limb soup is defined? Or do I have to tell it? You guys know, right? So when you have a sequence, you can take its limb soup by first of all you take the supremum of the tails. For example, you can take Cn to be, let's say, for example, mod of An 1 over n, mod of An plus 1, 1 over n plus 1, and so on and so forth. You can take this sequence, sorry, Cn to be supremum of this, supremum of this. So clearly you can see that this Cn, if your An is bounded or unbounded, we don't care. If it is unbounded, this supremum is going to be unbounded. So if the sequence is unbounded, this sequence is going this if this sequence is unbounded, the supremum is also will be unbounded. But if the sequence is bounded, then you can see that Cn is going to be a non-increasing sequence. And since your actual sequence is bounded, so your limit of Cn, since it's non-increasing and bounded, that will exist, and therefore you will get a definite limit, and that is what I am saying, that that is what it's going to be, our 1 over r. Okay, so 1 over r is what I am saying, limit of Cn. Okay, it's one and the same. Okay, fine. Okay, so how do I prove this? What we are going to essentially use is, it's going to be very again we are going to have this geometric series kind of ideas, and let us see. Okay, so we use the following fact. So let me just erase this thing. Okay, so proof. So I'm going to use the following fact. You can tell me which you know or not. So this is essentially root test. Okay, so what was root test? If I can recall for you guys. So root test was that if I take Bn is a sequence of non-negative real numbers, if a limb soup Bn to the power 1 over n, if this guy is less than 1, this implies summation Bn is finite. Okay, so and if limb soup Bn to the power 1 over n is bigger than 1, this implies n Bn is actually equal to infinity, I can write. So let me just write, it does not converge. Okay, so this will be actually equal to infinity, in the sense that this will summation Bn will diverge to plus infinity. Okay, so this you know, right? Yeah.
Yes, sir.
Yes.
Yeah.
Yes, sir.
This is something which is very easy, because the moment you have limb soup to be less than 1, you can just find some r which is between this limb soup and 1, and then you can use comparison test with geometric series, and you will get the result. Similarly, the other one as well. Okay, so now what we are going to do, we are going to do the following. Okay, so let us say I want to prove the I want to find out the radius of convergence of a n z power n. So what we are going to do, we are going to put the following thing. Okay, so for Hadamard's formula, we take Bn equal to mod of an r power n for some r bigger than or equal to 0. Okay, so this is what I am taking, r bigger than or equal to 0, some real number. So that is what I am taking in this case. Okay, so if I have this like I'm choosing this Bn over here, and now if I apply our theorem, then what do I get? Then we get that if mod of an r power n whole power 1 over n is less than 1. Sorry, I should have written lim sup. Lim sup. Lim sup of this guy is less than 1. This implies that summation mod n r power n is finite. Right? I get this one. Agreed?
Yes, sir.
Now this is what? This is nothing but r times lim sup of mod of n to the power 1 over n. Correct? Yeah. So I see that if I have this property, then this is convergent, and this is equivalent to saying that this is equivalent to saying that lim sup of mod of an to the power 1 over n is less than 1 over r. If that is happening, then mod of an r power n is finite. Agreed?
Yes.
And similarly, if lim sup of mod of an r power n whole to the power 1 over n, if this guy is bigger than 1, then this guy is it's not convergent. So this is actually equal to infinity. So this implies means I can say that this condition is equivalent to saying that lim sup mod of an whole power 1 over n, and this is, if this is bigger than 1 over r, then that implies mod of an r power n is equal to infinity. Okay, so I have this. So we notice these things. Okay, now let us come to the set S. So what was the set S? The set S was set of all r positive such that mod n bigger n an r power n, an in absolute value, this is finite. Okay, so from here it should be clear to you what is the threshold. So S is this guy, and my radius of convergence is supremum of all these sets. So now try to understand, the moment this quantity is less than 1 over r, this quantity is finite, and the moment this quantity is bigger than 1 over r, this series is equal to infinite. Okay, so therefore it turns out that if I look at this set, only those r qualifies for which lim sup of an is an to the power 1 over n is less than 1, right? And the ones for which bigger than, if it is, so that means, so if r bigger than 0 is such that r is less than 1 over lim sup of mod of an to the power 1 over n, then r belongs to S. And if r is bigger than 1 over this lim sup, I am not writing the full expression, then r does not belongs to S. Okay, so now therefore what do you think, what is going to be the supremum of S? Yeah, I have got 1 point. So if I take any r less than that point, that r is in capital S, and any r bigger than that point, then that r is not in my set S. So therefore what will be my supremum of S?
Lim sup.
Uh,
Lim is
1
supremum.
upon
One.
lim sup.
Lim sup.
Yeah, not lim sup, hence 1 upon that. Hence
One by
1 by 1 by.
lim sup of mod of an to the power 1 over n. Agreed to all of you? All of you, do you agree to this?
Yes, sir.
And by definition, what's my radius of convergence? By definition, my radius of convergence is equal to supremum of S, right? So this is R, which is equal to supremum of S, which is equal to 1 upon lim sup n to the power 1 over n. So if you just here you can also invert it, doesn't matter, because we are going to here allow this thing could be equal to 0, this thing could be equal to infinity, whatever you wish. We can have several such possibilities. So depending on that, your R could be anything. Okay, so yeah, anyway, so therefore we get the desired formula. Okay, fine. Is this clear? Okay, so this formula that we write over here, this is valid on close 0 to infinity union infinity. Okay, so infinity. So that means I am allowing that one of them can be 0, one of them can be plus infinity, and vice versa. Okay, one of them can be plus infinity, one of them can be 0, doesn't matter. Okay, so in the extended sense also this is true. Fine, so we get this formula for the limb soup. Okay, great. So you can use this formula to figure out the limb soup of various power series. Okay, so for example, if I take the power series n power n into z power n bigger than or equal to 0, let's say. So what will be the uh, radius of convergence? What will be value of R in this case?
1.
0.
Just be careful a little bit.
0.
Yeah.
Zero.
So what is an to the power 1 over n? So that's just n. So lim sup of that is infinite. R is 1 upon that. So this is 0. And so you see, I can have R to be equal to 0. That's a possibility. And for example, if I take z power n divided by n factorial, then for this power series, you will be able
Infinity.
to, R is going to be infinity. Okay. Anyway, so there could be all extreme possibilities, and we have already seen these ones. You can verify if you wish. So for all of them, R is equal to 1. Okay, but of course, on the circle, like mod z is equal to R, all these three have different behaviors. Okay, so this is something which we get, and so therefore we now understand how to calculate this radius of convergence, and we also have a formula. Okay, so I am going to leave you with an exercise which will give you an alternate formula for this radius of convergence. So if so let a n z power n be a formal power series if mod of an plus 1 divided by, or let me write the other way around, if mod of an divided by an plus 1 exists, if limit n tending to infinity mod of an divided by an plus 1 exists or equal to infinity, then R is equal to limit n tending to infinity mod of an divided by n plus 1. Okay, so you can have another formula. This is exactly again in the actual proof of Hadamard's thing, I had used root test. Here what you have to use is the ratio test. Okay, so I am assuming that the ratio is having a limit. Generally in ratio test you take n plus 1th term divided by nth term. Here I am taking the reciprocal, and if that ratio, if it has a limit or if it is equal to infinity, depending on that you will get that your radius of convergence is that particular limit. Okay, so this is one exercise which I am leaving for you to do, and you will be able to do this. Okay, great. Okay, so yeah, let me just do one thing. Yeah, okay. So what I want to say is that the following. So let me also give you another exercise. Yeah, so for example, how how can we so let us say we have two power series, each of which is having a radius of convergence, and then can I say something about the radius of convergence of the product or the sum and things like that. So this is the exercise regarding that. So let summation n bigger than or equal to 0, a n z power n, and summation n bigger than or equal to 0, b n z power n be two formal power series, okay, whose radii of convergence is at least r bigger than or equal to 0, then the power series or the formal power series, let me write formal power series Cn z power n bigger than or equal to 0, comma Dn z power n also has radii of convergence at least r, where what is my Cn and Dn? Cn is equal to An plus or minus Bn, doesn't matter which what you take, and Dn is equal to the following. So Dn I have to define slightly carefully, I from 0 to up to n, ai Bn minus I. Okay. So what I'm saying is that if I have two power series whose radii of convergence is given, which is at least capital R, then you will be able to say that if you take their sum or you subtract them, that whole thing is also going to have radius of convergence at least R, and the Dn is obtained by taking product of these two power series. Okay, so when you take product of two power series, the product of course very naturally does not become that coefficient wise you just multiply and you get. So product of multiplication of power series works exactly like multiplication of polynomials. Okay, so the way you would have multiplied a polynomial and you would have gotten, so exactly in similar way you would multiply power series and you will get coefficient. So in at the formal level itself, one can do it like this, and then you can say that those formal power series are going to be having radius of convergence at least r. Okay, so where r is the let's say minimum of the radius of convergence of an z power n and bn z power n, and and moreover on b open 0 r we have, what do I have? I have that summation n bigger than or equal to 0, Cn z power n is equal to summation n bigger than or equal to 0, an z power n plus n bigger than or equal to 0 plus or minus bn z power n, and summation n bigger than or equal to 0, dn z power n is equal to n bigger than or equal to 0, an z power n times n bigger than or equal to 0, bn z power n. Okay, so this radius of convergence has this property which works in this way for the power series like this way. So if you add that and if you take their product and things like this, you will get this kind of a phenomenon. Okay, so is this clear? So this is a simple algebra of power series which you should keep it in mind and you will be able to prove this. Yeah, tell me.
सर Cn वाला रिजल्ट थोड़ा सा डाउटफुल है, एटलीस्ट Cn एक्चुअली जब जैसे कि सपोज लेट अस सपोज कि एक सीरीज ले लेते हैं an zn एंड सेकंड सीरीज आल्सो an zn, देन दोनों का डिफरेंस ले लेते हैं तो Cn तो जीरो सीरीज बनेगा।
हाँ, तो वो तो सब जगह पे कन्वर्ज करेगा, तो एटलीस्ट R पे तो कन्वर्ज करेगा ही ना, isn't it? At least on B0R it will converge, right? Isn't it? I am saying at least. So my radius of convergence is at least that much. It can converge beyond that as well. Okay. I am not saying that is the value of the radius of convergence. Please be careful here. I am saying that the radii of convergence is at least. Okay, clear? तो उससे बड़ा भी हो सकता है.
Yes, sir.
तो वही. Okay, so is it clear whatever is the question Abhishek was asking and the statement whatever it says? Yes.
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 Yes, sir.
So this is something which is rather elementary, which you will be able to do. Okay, so now what I had started with power series for the following reason is that we said we are going to see them as non-trivial example of holomorphic functions. Okay, so I am going to do that. Okay, and I will prove a theorem regarding this. Of course, the proof we will see it in the next class, but today let me state the result, and we will try to understand the statement, and in the next class we will prove this. Okay, so this is power series gives holomorphic functions. Okay, so what's the theorem that I have here? Let me write down the statement and then we will see how we can prove this. Okay, so let summation n bigger than or equal to 0 a n z power n be a formal power series with radius of convergence. Okay, r which is positive. Okay, so here of course if the power series does not even converge in a disk, there is no point. Like if it converges only at point, for example, if I take so where did I see? Yeah, if I take this power series n to the power n times z power n, so here the radius of convergence is 0. So this power series converges only for z equal to 0. So if it makes sense only at one point, anyway, I am not going to talk about holomorphicity there. So that's not of much interest. So we are always going to take power series with positive radius of convergence. You can take power series to be with radius of convergence to be infinite. That's absolutely allowed, but you should at least have the radius of convergence to be positive. Okay, then what's the first thing? Let me write down. Then the first thing is that for each k bigger than or equal to 1, the series, okay, or the formal power series, whatever you want to say, n bigger than or equal to k, n into n minus 1, so on and so forth, n minus k minus plus 1, a n z to the power n minus k also has radius of convergence r. Okay, so let us try to observe. I have a n z power n, a formal power series. I'm having a radius of convergence which is positive, r positive. So on that the power series converges. So that gives you a function, and we are interested to figure out or say that these functions are holomorphic functions. So for that, the first statement what I am making is that this new power series which I have written for all k bigger than or equal to 1, n into n minus 1, so on and so forth, n minus k plus 1, a n z power n minus k, this also has radius of convergence r. Okay, so can you now for example in your head, do you see how do you get this power series? For example,
By
from the
differentiating. By
absolutely
term
very
wise
good.
differentiation.
Absolutely, by taking term by term differentiation of the power series that we have started with, we are if we do term by term differentiation, we are going to get this. Okay, so that's the first statement, number one. Number two, once you have realized that, let me say this: for any a in C, the function fz defined by summation n bigger than or equal to 0 a n z minus a whole power n. Okay, so far I was taking formal power series, so it was I was having only one means I was having indeterminate z, but now I am taking power series around a point. Okay, so this power series is infinitely differentiable, or the function is infinitely differentiable in BAR. Okay, so this BAR means set of all complex numbers z such that mod of z minus a is less than r. So in this uh, open ball, the function f of z given by this power series centered at a this time is going to be infinitely differentiable. Okay, so it's not only going to be differentiable but infinitely differentiable, where and the kth derivative of f at z is given by exactly what you anticipated, n bigger than or equal to 0, n bigger than or equal to k, n minus 1, so on and so forth, n minus k plus 1, an z minus a whole power n minus k. Okay, for all k bigger than or equal to 1 and mod of z minus a less than rho. Okay, so if I take any point in that open BAR, it doesn't matter how many times you wish, you can keep taking this derivatives, and you will still have that all those derivatives are going to be make sense. The function is going to be infinitely differentiable, and the derivatives are also given by in terms of power series, which you can see. Okay, and so that is what we are going to, this is the theorem that we are going to prove in next class. So this tells you that power series, these are very special examples. Of course, these are holomorphic functions and all that we see. Not only that, so what we see that they are infinitely differentiable. Okay, so far we had defined holomorphicity by just saying that it should be differentiable in a neighborhood, just like there was no additional condition other than this. But what it turns out that power series are even much more stronger. They are going to be infinitely differentiable. Okay, so as far as, for example, in case of real analysis, you have seen that there are functions which are, for example, differentiable, but the derivative is not continuous, and or maybe one time differentiable, continuously differentiable, but then at the second time it's no longer continuously differentiable. So there are these functions, C1 functions, C2 functions, C3 functions, so on and so forth. You have C infinity functions also, like who are infinitely differentiable and all that. So you have so many notions there. Well, what we see is that these power series, like they are, I was trying to say that they are going to be holomorphic, so that means they are going to be differentiable, but it turns out they are much more than that. They are going to be infinitely differentiable. Okay, and in fact, you will see that this is something which will happen. This will be true for all holomorphic functions. We will see later that all holomorphic functions on subsets of C are going to be infinitely differentiable. Okay, so therefore there is no concept of C1 function when we think of holomorphic functions on C or subsets of C, open subsets of C. So we don't have this concept of C1 functions, C2 functions. All of them are infinitely differentiable. Okay, so that's a very, very powerful statement that we see for power series. Okay, so is this clear, the statement that I have made?
Yes.
Yes.
Yes, sir.
Okay, fine. So pondered about this a little bit. We will see how we can prove that in the next class, and I'll take it forward from here. Okay, so that's all from my side for today. And if you have any other questions, I can take that. I'll stop the recording.
So